Okay, so we're looking at this problem, and I'm in the middle of helping someone. He may pop in and ask questions, but I'm going to keep this recording forever now. So, Luke, just to let you know, you may be in future generations.
No worries.
Okay. So we do just like we always do, we find our power series for y, y prime, y double prime. But we're going to have to distribute these factors here inside of those. So we're going to have six different terms we're going to have to keep track of here. So the 5 just comes along for the ride, but this x is going to raise my exponent up by 1. Here, the 1 just comes along for the ride, but this minus x, I've just brought the negative in here for the minus, and notice my power went up by 1. And then same game over here, the minus 2 and the minus 2, but this x, when I multiply it in, I'll now get an n plus 1. All of these need to have the same exponent. They all need to be in or whatever, and they all need to start at the same place. So this guy here, let's do these one at a time. If I plug in n equals 0, my starting, this whole thing is 0. If I plug in n equals 1, the whole thing is 0. So I might as well start counting at 2, because the first two were 0 anyways. Why did I do that? Because I want to raise these up by 1, 2, raise all these up by 2. If I'm raising these by 2, I have to drop this by 2, and I can't have negative n values. So that's what I've done. I've restarted counting at 2 because the first two were 0 anyways. And then I raised all these up by 2 while dropping that down by 2. And you can check and see that we get the same thing. If I plug in n equals 2 here, the first one that counted, I get 2, excuse me, a2 times 1 times 2 times x to the 0. If I plug in n equals 0 here, I get a2 times 2 times 1 times x to the 0. I get exactly the same thing. These are the same. Okay. This guy here, I could do the same thing, but I'm never allowed to have negative n's. I only want to drop these down by 1, so I'm only going to kill off one of the startings, if that makes sense. When n equals 0, this whole thing equals 0. That's also true when n equals 1, but I'm not going to get rid of the n equals 1 because I only want to raise this up by 1. I want this to be a 1, so I can raise this by 1 and drop that by 1. So I'm going to start counting at 1. And again, the reason I can do that, because when I plug in n equals 0, 0 times anything is 0. So get rid of the n equals 0. It was 0 anyways. Raise all of these n's up by 1. Simultaneously drop that by 1. Okay. This guy's already good. He's not. I'm going to do the same game to him that I did to him. Exactly the same game. Start counting at 1 because n equals 0 doesn't matter. Raise these by 1, drop that by 1. So that's 3. 4 was already good. He starts at 0 and has x to the n. 5's already good. 6 is a problem. He's one bigger than everybody else. So I'm going to have to handle 6 by himself. I'm going to have to make this an n, so I need to lower all these by 1 and raise this by 1. All the powers have to match. They have to all be x to the n. Doing that messed up one of these guys. Now he starts at 1 instead of starting at 0. There's no way to make number 6 match everybody else. It's impossible. So now I got to play a different game. This guy doesn't have an n equals 0 term. So we're just going to ignore him for a minute. We're going to use everybody else and plug in n equals 0 and see what we get. Into each one of these sums, I'm going to plug in the n equals 0 term. I'm breaking that off and doing it by itself. So plug in 0 for all the n's. Like even here, x to the 0 power is just 1. 0 plus 1, 0, n plus or 0 plus 1, and so forth. And that has to all equal 0 because I got to go back to the original. On the other side, all of my terms are 0. So in particular, the n equals 0 term is 0. So I just broke off the n equals 0 term because the first 5 had an n equals 0. Set that equal to 0, and I can solve for A2. Then, since I've already used up the 0, now these are all going to start at 1. I just dealt with the n equals 0 term by itself. Now I can combine the rest of them together, starting at 1. So that's all I did in the next step. Combined all of this together into one sum because they all have x to the n. And they're all going to start at 1 now. Then I can get my recursive formula. Remember, this is really 0 x to the n, or the sum of 0 times x to the n.
Oh, that's how the x to the n drops
Right,
for
because
from
this
the next
is
part. Okay.
0 plus 0 times x plus 0 times x
10.
squared plus
Okay.
z. Right. So for
Right. Okay.
every power of n, my coefficient over here is 0.
Okay.
Okay, and then I solve and get my recursive formula. And this is what I'll have to use to get all the rest of my a's. A2,
Okay.
I had to get individually by breaking off that first term, that 0th term, from everybody that had it and ignoring the one that didn't even have it.
I see. You can just do that. You could just leave it
Right,
off and solve for A2 because you already have A0 and A1.
right, right. Think about if we wrote all of these out, this would have, when I plug in n equals 0, I'm going to get an A2. When I plug in n equals 0, plug in n equals 0 everywhere, I'm going to get a whole bunch of stuff equals 0. Then I would plug in n equals 1 everywhere, n
Right.
equals 2 everywhere, and so forth. Just when I plugged in n equals 0, there was nothing to plug into this one, so I just ignored it.
Okay. Then you just solved
Yep,
like a normal one.
yep. This breaking off one of the extra ones happens whenever your y gets multiplied by an x.
Right.
These actually help. Multiplying your y
Yes,
prime, your y double prime, that
I
can
agree.
sometimes make it easier. Multiplying your y by an x can make it much harder because you end up with this, the n
That
plus
that
one.
neck.
You end up with that
Right.
n
Yeah.
plus one, and it's impossible to make everybody else match him.
Right.
Okay, does that help?
Yes, that helps.
All right. I'll stop recording and I'll post this for everyone.